Thank you all, and particularly thank you to Brian and Ben for doing such a great job of running the accelerator. I'm extremely excited to present to you all EDAC Labs, electrochemical direct air capture of CO2. We've developed a pathway to truly scalable atmospheric CO2 removal that's electrically driven, interruptible, energy efficient, inexpensive to build and operate, and closed loop. Electricity and air in, CO2 for sequestration or use out. Slide. I've been involved in the DAC space since 2013, when us crazies could fit in a small conference room and did, continually searching for an approach to direct air capture that could truly scale. I've started $1 billion worth of hard tech electrical and chemical companies, so I think I have some clue what's scalable and what isn't. So I'm particularly thrilled that we're launching EDAC Labs based on development, and Chao Wang, who you just heard about at Johns Hopkins. We've been working through the accelerator for the last 8 months with Professor Chao to refine his technology and create a continuously operating capture system. The technology has been under development for 2 years, and that technology builds on Professor Chao's expertise in electrocatalysis and chemical engineering. Well, this page only has room for the two of us. We have a highly qualified COO and senior scientists waiting to hop on board as part of our launch. We've had extensive discussions with potential collaborators on scaling the engineering and development of large air contactors, which are a critical part of our solution. Slide. So why DAC? I think you've all heard about the Paris Accords, IPCC reports. You've probably seen this kind of graph showing the need for massive scale active CO2 removal to hit carbon neutral by 2050, whether it's tens of thousands of metric tons per annum or billions of tons or gigatons, it's all the same. By 2050, we'll have put at least 2,000 billion tons, it's 2,000 gigatons of CO2 into the biosphere. Unless we actively remove CO2, we can't stop the Earth from warming. Well after 2100, which you always hear about as a date, even if we stop adding CO2 tomorrow, the average residence time of CO2 in the atmosphere is 100,000 years. And it doesn't matter if it went in 100 years ago or tomorrow, it keeps warming the planet. It's not like pollution that washes out with the rain. We have to actively remove it, and DAC is the most scalable of those technologies. Just to give you a perspective of the scale of this whole problem and the opportunity, a single gigaton of coal, which is largely carbon, would occupy the Washington Mall from the Jefferson Memorial to the Capitol to the height of the Washington Monument. Actually 10 times the height of the monument for a single gigaton. So just as the problem and the opportunity are massive, so are the physical resources have to go into solving it. And that's why I think our approach is so critical. Next slide. You know, our technology is deceptively simple. We apply electricity in an electrodialysis cell to separate the ions of table salt and water. That creates an acid and a base. Electrodialysis is a well-established industrial technology used in other purposes in the food and pharmaceutical industries. It has a solid supply chain. You can buy the membranes off the shelf. We don't have to create them. This basic solution runs through a specialized air contactor where it absorbs CO2. That bases aggressively absorb CO2 has been known since the dawn of chemistry. But our air contactor allows molecules in the air, particularly the CO2, to diffuse into the liquid, but not the liquid to mix with the airstream. By avoiding the direct mixing, our active solution doesn't get contaminated with debris in the air, and we minimize water losses. We then combine the salt and the acid in a reactor. This releases the CO2, it reforms the salt, and back it goes into electrochemical cell in a continuous closed loop. As I said, it's deceptively simple, but it's not so easy to get a balance. And yes, there is a trick in here that we're hiding until we finalize our IP for it. So why is this such a big deal, and how does it differentiate? Well, I think we've solved some of the largest impediments to wide-scale DAC. One, we operate roughly at ambient temperature and pressure. So most of our system can be built with plastic. It's a big deal. No stainless steel reaction vessels, no difficult to weld metal piping. It's lightweight, and it has a low CO2 footprint. which is critical for gigaton scaling. We only use electricity as an input, and we're highly interruptible. That allows us to use renewable energy. The energy needs of DAC are unfortunately massive. So trying to do a DAC solution that needs 24 by 365 power doesn't scale. We can help stabilize the grid, not destabilize it. Lower energy usage. We use half the energy of the current leaders in this technology. And again, we can use interruptible renewable energy. We isolate the active chemicals from exposure to contaminants in the air. To perform DAC, you have to move massive, massive volumes of air. There's lots of rocks, particularly if you're going to put it in a desert environment, dust, pollutants, pollen, and just crap in billions of cubic feet of air. We stop the direct contact of the dirty air with anything sensitive, particularly our electrochemical membrane, allowing a closed loop in our reactive chemistry. We have a closed mass balance. We don't keep adding anything except electricity, since we've largely eliminated water losses. This creates something that's inherently modular, containerizable design that we think leads to mass production and easy deployment. This matters as we need to build millions of capture units a year to solve the climate crisis. We believe this approach is the only one that can scale and reach the sub $100 a ton goal the US government set for its moonshot target. And we think we can get there as soon as 2025. So what does $100 a ton mean? It means mitigating the climate crisis for less than $1 a gallon of gasoline. We think these advantages are compelling and dramatically different from other approaches, which we'll talk about later. Next slide. So the market, I'm not going to talk about it much. It exists today. It's rapidly growing. There's bipartisan support. And if we're going to make a dent in global warming, it has to become one of the world's largest markets. Oh, we roast. So the one note, and it's on the slide, $100 a ton, 1 gigaton is $100 billion. 10 gigatons, it's $1 trillion a year. Market's not the issue. Scaling the right technology is the issue. Next slide. So I just want to take a minute about competition, primarily to emphasize again how our approach is slightly different. These are all high-profile companies in the DAC space with recent funding announcements. I also want to step back for a second. When we talk about sequestration and capture of carbon, there's also the side of disposal. Disposal is not a problem. It can be done for about $15 a ton. We've been doing it for 50 years. We've now put billions of dollars toward carbon hubs precisely for this purpose. All the companies in the slide are doing, we're doing, making capture devices. So Verdox, they've created a specialized membrane, claim very, very low energy efficiency, but they have to create millions of square meters of an electrically and chemically active membrane. And that membrane, because you can't put HEPA filters at the front end, all you do is change filters, is going to get directly exposed to everything in the air. I wish them luck. Mission Zero is somewhat similar approach to ours, but we with a different and more complex chemical, active chemical. Climeworks just got $650 million. You've heard about in Iceland. They use steam and vacuum to release CO2 captured on solid absorbents in chambers. So it requires a lot of heat, plus its absorbent is fully exposed to the air. You also can't turn the power on and off while you have heavy heat because you lose a lot of energy, so you can't use uninterruptible power. Carbon engineering has a base to capture CO2 just as we do, but it's exposed to the air, so they have to design to avoid blow-off of a caustic solution. And they have water losses to worry about. And then they do a more complex cycle that, among other things, involves 900 degrees C temperatures to release the CO2. They have a $900 million plant under construction. It uses natural gas to provide the heat and captures that CO2. And it uses about 3 times the energy we think we need. Heirloom, recent company, very low cost materials, reversing the cement production cycle. They also need 900 C's heat to release the CO2. That's about 2 times the energy we project. So we use low cost materials that exist. We shield our active membranes and we're low energy. Again, we think these advantages will prevail. Next slide. So where are we? One, in the Wang lab, we've got a continuously operating prototype It's still sub-kilogram a day level. We're expecting some additional pieces that we've ordered to come in to rapidly ramp that up toward a 10 kilogram a day goal by the end of 2022. We're finalizing an IP license agreement with Johns Hopkins. It'll be part of our kickoff for this company. We've been working already with development partners for system components, and we're going to start real system development toward a 1 ton a day plant by the end of 2022 for the development, but we expect to actually put in operation a plant by 2023. We're seeking $1.5 million basically for startup purposes, establish a base of operations, get our first full-time employees outside of sponsored research, which we'll also be doing. We're going to leverage our initial capital with grants from DOE, DARPA, and others for non-dilutive capital, which we already have some interest in. And we're going to position ourselves for a serious seed fundraise by 2023 to implement a real scale. So thank you. Next slide. That's it. With your help, we can save the world and make money at it. We hope you'll join us.
Thank you.